All right, hi everyone. My name is Ezra, and my talk today is called Interruptible Software. And if we look at the screen, hopefully this makes sense. If you have an automated process, wouldn't it be nice if you could go play, like start the process, pause, stop where you are, resume, and then you can continue where you left off, just like a music track. So no matter which workplace I go to, there are always these two processes. One's the build process, where we build our application, and one's the deployment process, where we deploy the application to some environment. And it's not always 4 steps. Usually there's hundreds of steps in there, and they can all fail at different points. Now, let's look at the execution of any process. If we look at manual execution, for the deployment process, you might launch some servers by asking a different team to give you some virtual machines. You might ask some cloud provider to give you some virtual machines, or you might have some actual hardware. With the application upload, you're probably going to copy that by SCPing or using some sort of file transfer. Then you configure your app, whether that's by a text file on disk, or whether you start your app first and then configure it through the UI, and you might start your app. Now, when we go from manual execution of a process to automatic execution of a process, we switch from doing each step ourselves to having a tool, which may be a shell script, maybe some cloud provider provided tool, or some in-house built tool, which does all the 4 steps. But our role as a human is to provide parameters to this tool. And we provide parameters, press go, and the tool hopefully does all of these steps. Now, in the manual execution, if we made a mistake for configuring the app, we can go from step 4 back to step 3, change the configuration, go back to step 4, restart the app. If we were to upload a new version of the app, we can go back to step 2, upload the new version, maybe configure it again for the new version, and then start the app. But with the automated process, what we tend to do is, if we have any mistakes, we can't stop the process where it is. We need to wait until it's complete. We might have to clean up the whole process and fix up parameters and start again. So wouldn't it be nice if you could pause, right? Let's say you started the process, and has anyone started a process and go, oh no, stop, because I got something wrong immediately? Because that's a completely common scenario with bash scripts, right? Shell scripts. So let's look at a bus analogy. Imagine you are going to take the bus and you lost your phone. You realize, oh, I don't have my phone, right? Pressing on. And there's 3 points in time where you might realize, I don't have your phone. I don't have my phone. The first point is before you get on the bus. The second point is when you're on the bus. And the third point is after you get off the bus. And if you're not on the bus, which is before you're on the bus or after you get off, it's safe to just go look for your phone. But if you are on the bus, then it's not safe to just jump off, because you might get injured, right? So ideally, you could stop the bus or interrupt the bus, wait for it to stop, and then get off, go look for your phone. Now, if you think about this in terms of software, non-interruptible software is like a bus with only 2 stops, the start and the end. And if you want to interrupt this kind of software, it's like jumping off the bus as it is moving. Whereas interruptible software is introducing the stop button and bus stops to that journey. And if you realize something's wrong, you can press the stop button, wait for it to stop, and get off. So the bus stops are your safe stopping points. Actually, there are 2 concepts here. The first is stopping, which is interruptibility. We need to stop safely. And once we've found our issue, we want to resume from where we left off, because we don't want to pay the journey, pay the price of the initial start to where you stop the journey multiple times. ideally, you can just continue where you left off. So to design interruptible software, well, before we build any software, we should design it. Otherwise, you end up with a mess. Like the internet's quite messy, right? So ideally, we can design something good before we actually build it. So the first step for building an interruptible software is designing the stop button. So if we think about the different ways we build applications, whether it's command line, web, or desktop, ideally we can have an interrupt button which works on all three interfaces if we want to be that flexible. So what you don't want to do is you don't want to only rely on the operating system's interrupt signal, which might work for command line, but not for web application or desktop application. What you should do instead is, instead of listening for a Control-C, create an interrupt signal. Over here is quite simple, it's just a plain struct. And you want to listen to your application-specific interrupt signal. Because that way, if you're listening to your application-specific interrupt signal, when you come to designing the interrupt button across the command line interface, the web app, or the native app, you can translate between the different signal listening mechanisms, whether it's a Control-C or whether it's a web request which you receive from the sockets, or whether it's a user button handler. You can translate between that and your interrupt signal. So on the command line, you might just listen for the operating system's interrupt signal and then immediately send your application level interrupt signal. Whereas on the web or desktop, you'd have a request come in. You have to translate between the request and make sure it's an interrupt request. It should come with an execution ID for your process, and you look for the interrupt signal sender for that execution, and then send your interrupt signal that way. And so in this design, you can support all three interfaces. So this is our interrupt button. Now we need to know where to stop. So we've got a way to signal that we want to stop, but we need to find a safe place to stop. So the simple rule is, if you are executing a process, wherever you receive an interrupt signal, finish what you're doing and then stop there. Don't start anything else. And in code, it's from this trivial code where we run 3 steps, step 1, 2, 3. That's to insert these interruptibility checks before every step execution. So I know the code is not maintainable this way, but we'll get to that. So before you run any step, that's the point that you check. Was I interrupted? And if I was, then I will stop. And if I was not interrupted, then I will execute the next step. Cool. So before we go on, some of these steps might be big. So for example, if you have a file upload step and your file upload is a 10 gig file, or at least in part it's 10 gigs. If you want to have finer grained interruptibility, you can push that interruptibility check from the overall step executor down to the individual steps. So for example, if you've got a step which does 1 million units of work here, every 1,000 units you might check, was I interrupted? And if I was, then I will bail. That was an interruption. Right. So now, next thing we want to think about is parallelism. So if we tend to use parallelism as a way to improve the overall performance of our processes. So if we have multiple tasks executing in parallel or concurrently, you can apply the same rule as the serial execution. Whenever you receive an interrupt signal, finish what you're doing, don't start anything else. So in this case, I would finish here. And if I had 2 things in executing, then I would finish there. And finally, if I had those two, then I would finish there. And if you were interrupted on the last one, you might as well just finish. So the safe interruption rules, finish everything in progress and don't start anything new. In terms of concepts, there's not very much more complexity to serial or parallel interruptibility, but streaming over or iterating or streaming over multiple things, that's the hard part. So adding interruptibility to an existing iteration is not too much more work. Cool. Reporting. So when we write non-interruptible software, like one long execution process, we tend to care about the value that comes out of that execution. So we might execute the process and out comes a value. But when we start writing interruptible software, we don't only care about the value, we also care about what happens during the execution. So, for example, in the interruptible software variant, we're going to return an outcome, and the outcome is going to say, either I completed my execution, and here's my value, or I was interrupted, and there's no value. Is this screen size too? I mean, is the text too small? A bit too small, right? Let's zoom. But cool. So this is a basic outcome. I completed, or here's my value, and or I was interrupted and there's no value. We can be more informative and go, hey, either I completed the execution, here's the value, or I was interrupted, and here are the values collected for each step along the way. So that way, when we return to our caller, the caller can go, oh, the execution finished, let's continue and use the value to do whatever. Or the execution did not finish, at least I know what came out of the execution. And we can go one step further and not only collect the values that each step produces, but we can also track which steps did we do and which steps did we not do. And all of this is information that we are collecting so that if we want to resume this process, we have the information to pass into the process again the next time we run the execution. And so if we collect this information and save it somewhere, when we restart the execution, we can go, hey, step 1 and 2 were completed before, we don't have to run that. We still need to know what values they produced before, and we feed it into the next few steps. Cool, and before we look at implementation, there's one more thing we need to look at, which is strategy. So what strategy means is, just because I interrupt the process here, doesn't mean I want to stop just after the first step, right? So that would be the normal way. That would be the bus stop way, right? What if you could tell the bus driver, hey, I'm going to press the stop button, but I want you to stop two stops on the line, or 3 stops on the line. And even if I get on the bus, why can't I just press the stop button, hold it a long press, such that it stops me right outside work, right? Ideally, I don't have to be alert, wait for the 4th stop to pass, and then press a button for the 5th stop to stop the bus. Ideally, we could just set the destination at the start. So that's what an interrupt strategy is. If I wanted to stop after steps 2 and 3, I can tell it to do so. After steps 4 and 5, I can tell it to do so there as well. So that's what we want. And how this might look like in code is you have an interrupt strategy where you might ignore interruptions, which is if you receive an interrupt signal, you don't do anything, you keep going. You might have the finish current strategy, which is the simple one. We receive the signal, we'll stop on the next save point. Or we have the poll next end strategy, where if you tell me the number of steps you want me to continue doing, I will poll that number of things after I'm interrupted and continue, and after I've done all of those steps, then I will stop. Now, can anyone think of why this is useful? No? All right, so, so this is useful in testing. So if you have a 100-step process and you want to make sure that all your users, no matter who they are, they can stop at any point in that process, you want to test your interruptions at every single point. So you should go, let's interrupt my automated process, and let's tell it to stop after step 1, after step 2, after step 3, all the way up to 99. And that way you can guarantee that whoever's using the software, they can stop it, and it's going to be safe. It's not going to like mess up the environment. Cool. Now, we'll look at some implementation. So this is the no interruptibility version of an executor. We do step 1, 2, and 3. Quite simple. And we saw earlier the basic interruptibility, where we check for interruptibility before we do each step. But this is not maintainable when you have like 200 steps, right? And your code is never going to be one line for each step. It's going to be indented all over the place with conditions. So ideally, we can do something better like this. So we have all our steps inside some sort of collection. We iterate over each step. And before we execute the step, we check for interruptibility. If it's not interrupted, then we'll do the step. But if it is interrupted, then we'll fail. So this way, we don't duplicate that interruptibility check everywhere. So let's hopefully this live demo works. Network error when attempting to fetch resource. Oh, now it works. Yes. Okay, so we'll look at the code briefly in this side. So we've got a main method which runs execute, and it passes in true as its first parameter. And execute will iterate over step 1, 2, and 3, have our interruptibility check, and if it's not interrupted, then it'll execute these steps. And to make it realistic, steps 1, 2, and 3, they take in different parameter types. So this takes a boolean and returns a number. Step 2 takes a number, returns a float. Step 3 takes a float, returns string. So as close as possible to some real code which has different types. Now, if we were to run this demo, you can see, that steps 1, 2, and 3 were executed. I'll drag that over a little bit. Yeah. So steps 1, 2, and 3 were executed, and they passed values between them. And if I were to say, I want to interrupt after 2 steps, when I run the demo again, you'll see that it gives step 1, step 2, and then main says I'm interrupted. And if we do that for just 0 steps, we'll receive an interruption before we execute anything. So the point of this demo is to show that if we want maintainability, we can have interruptibility without sacrificing maintainability. So there is magic to turn functions which take different parameters into that into a generic type which can be iterated over, and that magic, it does take a while to learn, but then once you've got that, then you can maintain the true goal, which is I want interruptibility.
Sorry, just
Yep.
is that risk type? So can you?
Yes, it is. So if we look at the step function, let's expand the eye. All right, so can you read that soon enough? Okay, so step actually is a function which takes in another function, and it boxes it up and puts it into a step erased trait object. So that way, there is magic there which says whenever I have a step erased, then I can call some method on there, and it will delegate internally to the original function. And we might look at this at the very end when we've got time. Yeah. Yes, I know, it was very interesting to do this. All right. Where's my buttons? There we go. Okay, so we've got interruptibility, which is the first half of that process. We want to now resume our execution. So resumability is once we start a process from executing, how can we get back to where we were before? Because if we restart the execution and we change parameters for the third step, for example, we don't want to pay the price of the first part of the process again and again. Because if you are fixing a bug which occurs late in the automation, you don't want to have to run the automation from scratch every time. Because if you have ever managed some cloud environment, you know that deploying an environment takes ages, and you're just waiting for that server startup, like halfway through, right? And you might be waiting half an hour. So why pay the half an hour cost every time you change a little bit of code for that step in the future, right? So resumability is about resuming starting when you start. Cool. So how do we achieve this? Now, there are two main designs I've thought of. The first is the executor resumability, where the executor of all the steps handles whether I execute that step or not. The stepwise resumability is where every step decides whether it runs or not. So we'll look at some code for this. Cool. So executor resumability. Maybe one. All right. So for the executor to decide whether it runs a step, we pass in, instead of having just parameters as we did for the regular execution, we pass in an execution state, which will tell the executor, am I starting from a clean slate, which means I have to run everything, or am I starting from a halfway state, which means I have to run the other half, which I haven't run yet. And so when you grab the executor state, before you execute your steps, look into that execution state. If we start with a clean slate, then we'll run all the steps. Otherwise, if we start with some previous states, then we'll look at what steps were not done. Those are the steps that we will run now. And we need to also make sure that whatever got passed in for the previous state also carries the step values from the earlier execution, because we might need to pass information from step 2 into step 3. So we grab all of that, and then we run our regular execution. So this looks exactly the same as before. Cool. Any questions so far? Nope. So some pros and cons of this approach. There's a simpler API if you use the executor resumability, because all the interruptibility and resumability concepts are done within the executor. So all of the step logic doesn't have to care about the interruptions or resuming. But then the cost here is if your executor state contains stale information. For example, if your step launches a server and it's Linux version 20, right? And then someone's upgraded your Linux OS to version 21, then your saved state might be stale. And so if you reason over that stale information, you might just have a broken execution. But if you want to inform the user that, hey, you ran this process and the save state was Linux was on version 20, how do you check whether it's actually version 20 in the actual server? That's where the executor resumability design doesn't work, because the executor is so generic, it doesn't know to check this Linux server. It doesn't know what it's doing, right? So for that, we need to use stepwise resumability. So with stepwise resumability, every step knows what thing it's working on. And so with the previous state that you pass into the executor, we push each step's previous state, so the step-specific previous state, into that step. And the step can go, hey, you gave me this as my previous state. I'll start from there and execute if I need to. But because I have the previous state, I can also check, does the previous state actually match what is in my environment? And if it doesn't match, then we can signal that to the user. And in this sense, you get better usability, but you do need to pay the cost of development for that. If we look at the implementation, it's quite simple in the executor. There's no magic there. We just grab the step state from the execution state based on the step ID, and we pass that into the step. And if we look at let's look at the pros and cons first. So heavier API. So all step implementers need to care about interruptibility, because they may not need to know about the interruption signal, but they at least need to know about the resuming from a previous initial state. So it's not always a clean start. And yeah, the usage safety we mentioned before, if you have some initial state, you can compare it with the actual initial state. Cool. So here's a live demo, which just extends on the previous demo. And we'll look at the codes here. So we start with either a clean slate or some previous state. We can run both. And we pass that initial state through to the execute method. And within the execute method, we have our collection of all our steps. This time we need to have IDs for each step, so we know which state to pull out. And from all of the steps, we filter what to do, which is based on the execution states. We'll look at that shortly. And what all the steps are, we need to come down to which steps to actually execute, and then the parameters to pass into the first actual step to execute. So filtering what to do is, as we've seen before, if we have a clean slate and some initial parameters, then we'll start with, we'll have to do all the steps. So we just return the steps and the initial parameters. Whereas if we have a previous state, then we will have to do all the steps which we did not execute last time. So we just go, all the steps will retain if you are inside the collection of steps that were not done. And we'll grab the last parameter from the last step as the parameter to pass into the new first step. And we can run this. So we'll start with some previous state and run. And we can see that we run step 3 without running step 1 and 2. And in a simple demo, it's like pretty fast, but if you have 50 steps and you have to test step 51, it's really nice to just test step 51 without having to wait for the first 50 to complete, right? Because you're changing your code, and then you want feedback for the parts that you're testing and that you change code for. And so we want to reduce that feedback loop to just, I change some code, I see the effect that I'm waiting for, rather than having to wait for the first however long it is. And if we just went with the initial clean slate, it'll just run everything. There we go, step 1, 2, and 3. Okay, cool. Cool, so some real crates. So Interruptible is a crate I developed for adding interruptibility to streams. And so what this does is, for a stream of items, every time you have an item come out of the stream, adding the interruptibility to the stream means instead of you just receiving the item out of the stream, every item will be wrapped inside an interruptibility wrapper, which will tell you if there's no interruption, here's the item. Or if there was an interruption, you might not have an item, but you might. Because if you were interrupted before the first step, then there's no item. But if you were interrupted while you're processing something, then we'll tell you, hey, here's the thing that's was going to come out of the stream, but will also tell you that you were interrupted, and the stream will no longer return any values. Function graph is a graph library which you can run graphs of functions in parallel, and it integrates with Interruptible for that interruptibility capability. And the third here piece, that's my bigger project where it uses function graph and Interruptible to manage automation. So all of these are on GitHub if you want to look for them. Cool. So in summary, I've lost my train of thoughts. All right. So when we build software should enhance and not take away from the human experience. And when we went from the manual execution to the automatic execution, we gained speed, but we lost control. And interruptibility is just reintroducing the control that we took away. So I'd like to end with this note. In the world where everyone is building fast cars, design the brakes. Thank you. So happy to take questions.
It was an era. How's that ended?
So your depends on your use case. So what I do for parallel graph execution is I collect all of the errors as they come out, and I actually treat an error and an interruption quite similarly. So the interruption would go, I've got interrupted, and here are the values I collected. Whereas an error is I have an error, and therefore I'm stopping processing of everything else. So it's an error is in a way an automatic interruption. Yeah, and depending on how you run your stream, you can either keep running your stream and collecting the non-erroneous values, or you can tell your stream stop on the first error. But you need to have code within the stream whole function, I think it is, that to detect, is this an error item that I'm producing? And if it is, then stop producing more items.
So have you incorporated this into like process production somewhere?
In the process of doing that, so Interruptible and function graph, I recently published newer versions, but then the bigger project piece, that one has got those versions pulled in, but they are halfway, the code's halfway migrated. So once that code's fully migrated, then perhaps.
Not really a question, more of an insight. This looks and hopefully not like a lazy evaluation. It's just that you with explicit dunks and breakpoints at every turn.
Yeah, so one thing we tend to have with software is if we want to stop the process, we tend to have to like pull the plug. And ideally, well, to me it's annoying to have to resume from zero. So I'm like, is there a way to just do what we did before, like without having to start from zero? I want to continue where I left off, but at least see the value that we had at that point in time.
So these parameters that are coming from the steps, in real life, there will be architects that build products. How can those be preserved as again?
Yeah, so within the magic we had, every value that we need to save needs to be serializable and deserializable. Because for the state to be passed into that executor, we need to save it somewhere, right? And so to save it somewhere, that's serialization, and then to take it out of that saved state and put it into memory, that's our deserialization, and we need to have some magic there. We have solved this, where we can go, all right, if we know your step ID, then your step ID tells us how to deserialize that bit of data with that key. So we'll have step ID to arbitrary type, And then on deserialization, we use stateful deserialization, where when you deserialize that bit of the blob of data, it's going to first encounter the key, which will tell us the step ID. And the deserializer will go, I know I now have this key. Let me look up into my state. What's the deserializer to use for the value? And that's where we go, we need to make sure the user has registered step ID 1 has deserializer for a number. Step ID 2 has deserializer for a float or something like that.
See. Yeah, it's still thinking the artifacts are quite big one. Gigabytes of data. It's painful to serialize steps. They can be private.
Oh, actually, we
stored in some storage, just pass on references, right? It keeps.
yeah. Well, so if you store in some storage, you still need to. Well, for my use case, the steps are implemented by downstream users of the framework, and so we don't know the type that we're storing. Yeah, so we store it as whatever serialization format we're using. You can use some binary storage, but what I would do is I would store all the parameters and just deserialize it once at the start of the execution rather than between every single step. Yeah, at least that's the design I've chosen. May or may not be the best, but it fits the use case I've got it for.
I just one thing I keep thinking is that the properties of those steps determine the best execution. I guess strategy is not the word because you are using it, but best way of executing them. Like if those steps are side effects, maybe you need to undo them and you don't want to repeat them. But if they are pure, like you don't care, just like run it if you have the input. If not, you can save it or not save it. Or like if they are very fast, don't bother saving the input. You can just rerun them. Like if there are computations, maybe you want to rerun them only when the binary changes. So I was thinking as well, if I am using the piece framework, but I'm writing the steps myself, is there any way for me to inform the framework about the characteristics of my steps?
Yes, so the P framework itself does have a trait which the trait will define how well you design that trait will how well you design that trait will be how you pass information between the trait implementer, which is the consumer of the framework, into the framework. So that trait must be designed really well. And maybe I can bring it up here where if we look at, this is the actual trait. Let me just take that away. All right, so if we look at all of the functions, if I zoom in more, the trait itself will tell me the current state of the thing you're managing. Tell me the goal state that it should be. So this would be, for example, is the current state my server exists, or does my server exist with whatever version of some operating system? That would be the state current. State goal would be what should it be, and that's the way we pass information between the trait implementer and the framework. What's the difference between the current state and the goal state? If we can communicate all of these values, then the framework has enough information to determine, do I need to run the steps logic, which is like the heavy execution part, right? And if we don't have to run it, then we don't. And there are other constraints placed on the item, that's what this trait is called. There's other constraints placed on this trait such that if we need to present information to the user, we require the trait implementer to tell us how to present that information, and the framework will handle the rest. So whether we're presenting to a command line interface, whether we're presenting to a web interface, you just need to tell me, are you presented as a string of text or a number or a list of stuff? And we'll have to translate between whatever a list means to maybe a few lines on the command line or maybe some list elements on the web page. So the trait methods are probably the most important part of the design here.